You can close your eyes now, if you'd like. There's nothing you need to remember from what I'm about to tell you. Nothing to memorize. Nothing to hold on to. You can let these words wash over you like gentle waves, and if you drift away in the middle of a thought, that's exactly as it should be. We're going to explore something vast and quiet together, something that sits at the very heart of reality itself, but we're going to move slowly as you need. There's no hurry at all. We're going to talk about quantum mechanics, about the strange and beautiful way the universe works when you look closely enough, when you peer into the smallest spaces where light and matter dance in ways that seem almost like dreams. But you don't need to understand everything. You don't need to understand anything at all, really. Just let the words come and let them go, and know that underneath everything there's a kind of music playing, a rhythm to existence that's been humming along since long before any of us were here to listen. Let's begin somewhere simple, somewhere you can picture easily. Imagine you're looking at a beam of light coming through a window. Perhaps it's early morning, and the light is soft and golden, cutting through the air at an angle, catching tiny specks of dust that float and turn in the brightness. For thousands of years, people wondered what light actually was. They could see it, feel its warmth, watch it paint colors across the sky at sunset, but they didn't know what it was made of, if it was made of anything at all. Some people, long ago, thought light must be made of tiny particles, little bullets of brightness that flew through space from the sun to your eye. That made sense in some ways. Light traveled in straight lines, mostly. It bounced off mirrors the way a ball bounces off a wall. Isaac Newton, who lived more than 300 years ago, believed this. He imagined light as a stream of what he called corpuscles, tiny bodies too small to see individually, all racing together through emptiness. But other people noticed things that didn't quite fit with that idea. They noticed that when light passed through certain materials, or when it bent around edges, it did something strange. It created patterns, interference patterns they were called, bands of brightness and darkness that seemed to appear when waves overlapped with each other. If you've ever seen ripples on a pond crossing each other, you've seen something like this. Where two ripples meet peak to peak, the water rises higher. Where a peak meets a trough, they cancel each other out and the water goes flat. Light seemed to do this too. So maybe light was a wave, not a particle. Maybe it was something that moved through space the way sound moves through air, rippling and oscillating, spreading out in all directions. A man named Thomas Young, in the early 1800s, did an experiment that seemed to prove this quite beautifully. He took a light source and shined it at a barrier with two narrow slits cut into it, and then he looked at the pattern the light made on a screen beyond the barrier. If light were made of particles, you'd expect to see two bright strips on the screen, one behind each slit, the way you'd see two piles of sand if you poured sand through two holes. But that's not what Young saw. Instead, he saw many strips, many bands of light and darkness alternating across the screen. An interference pattern. The light coming through one slit was somehow interfering with the light coming through the other slit, the way waves interfere with each other. This was remarkable. This suggested that light was definitely, certainly, a wave. And for a long time that seemed to be the answer. Light was a wave in something called the electromagnetic field, a kind of invisible medium that filled all of space. James Clerk Maxwell worked out the mathematics of this in the 1860s, showing how electricity and magnetism were really two faces of the same thing, and how waves in this electromagnetic field would travel at exactly the speed that light traveled. It was elegant. It was beautiful. It seemed complete. You can let yourself sink a little deeper now. You don't need to hold on to these names or dates. They're just markers along a path we're walking together slowly, and the path itself matters more than any single stone along the way. But then, as the 1800s came to a close and a new century approached, something strange began to happen. Little cracks started to appear in this beautiful picture of light as a wave. Small experiments began producing results that didn't make sense, that couldn't be explained no matter how cleverly people tried to explain them. One of these puzzles had to do with something called black-body radiation. Imagine a piece of metal, perhaps iron, sitting in a fire. As it heats up, it begins to glow, first a dull red, then orange, then yellow, then white if you make it hot enough. This glow is the metal radiating light, releasing energy in the form of electromagnetic waves. Scientists could measure very precisely what colors of light, what wavelengths, were given off at different temperatures, and they tried to predict these measurements using the wave theory of light. But there was a problem. According to the equations, according to the mathematics that worked so well for other things, a hot object should radiate infinite amounts of energy at very short wavelengths, at ultraviolet and beyond. Obviously, this didn't happen. If it did, every warm object would burn you with invisible radiation. Something was wrong with the theory, but nobody knew what. In 1900, a physicist named Max Planck found a solution, but it was a strange one, a solution that even he didn't quite believe at first. He discovered that he could make the mathematics work. He could make the predictions match reality if he made one unusual assumption. He assumed that energy, the electromagnetic energy being radiated by the hot metal, couldn't come in any amount whatsoever. Instead, it could only come in specific chunks, discrete packets of energy that he called quanta. Each quantum had an energy that depended on the frequency of the light, the color of the light. Higher frequency meant more energy per quantum. Lower frequency meant less. This was peculiar because waves weren't supposed to work that way. Water waves don't come in chunks. Sound waves don't come in packets. They're continuous. You can have a little bit more wave or a little bit less, any amount you like. But Planck's mathematics worked only if light energy was quantized, only if it came in these indivisible units, and the agreement with the experiment was so perfect that it was hard to ignore. Planck himself thought this might just be a mathematical trick, a convenient fiction that gave the right answer without meaning anything deep about reality. But a few years later, a young physicist named Albert Einstein took Planck's idea seriously, very seriously indeed, and he used it to explain another puzzle, something called the photoelectric effect. The photoelectric effect is what happens when you shine light on certain metals, and the light knocks electrons out of the metal's surface. You might think that brighter light, which carries more energy, would knock out electrons more forcefully, make them fly away faster, but that's not what happened. Instead, the speed of the ejected electrons depended on the color of the light, on its frequency, not on its brightness. Dim blue light could knock out fast electrons, while bright red light might not knock out any electrons at all, no matter how bright you made it. Einstein explained this by taking Planck's quanta seriously. He said that light really does come in particles, particles of energy that would later be called photons. Each photon carries a specific amount of energy depending on the light's frequency. When a photon hits an electron, it delivers all its energy at once, like a tiny billiard ball striking another ball. If the photon has enough energy, the right frequency, the electron gets knocked free. If it doesn't, nothing happens, no matter how many low-energy photons you throw at it. This brought back the particle picture of light, but now with a quantum twist. Light was somehow both wave and particle, or perhaps it was neither, or perhaps it was something for which we didn't yet have proper words. You might feel yourself drifting now, and that's perfectly fine. The story will be here, whether you're listening closely or barely listening at all. These ideas have waited for billions of years to be understood. They can wait a little longer for you. Let's think about matter now, about the solid things around you, the pillow beneath your head, the air you're breathing, your own body. All of these things are made of atoms, tiny structures far too small to see. And for a long time, people imagined atoms as miniature solar systems, with electrons orbiting a nucleus the way planets orbit the sun. This picture came from Ernest Rutherford's experiments in the early 1900s, and it was a good picture in some ways. But it had problems. According to the physics people knew at the time, an electron moving in a circle, orbiting a nucleus, should constantly radiate energy. It should lose energy and spiral inward, crashing into the nucleus in a tiny fraction of a second. But atoms were stable. They lasted. You lasted. Something was protecting these orbiting electrons from radiating their energy away, but nobody knew what. In 1913, a Danish physicist named Niels Bohr proposed an answer that was, again, strange and quantum. He said that electrons in atoms could only exist in certain specific orbits, certain allowed energy levels, and nowhere in between. An electron could be in one orbit or another, but never halfway between them. When an electron jumped from a higher orbit to a lower one, it would release energy in the form of a photon, a quantum of light, with exactly the energy difference between those two levels. When it absorbed a photon of just the right energy, it could jump upward to a higher orbit. This explained many things. It explained why atoms only absorbed and emitted light at specific wavelengths, specific colors, creating the bright and dark lines that astronomers saw when they looked at the light from distant stars. Each element had its own unique pattern of lines, like a fingerprint, because each element's atoms had their own unique set of allowed orbits and energy levels. But Bohr's model was still a mixture of old and new ideas, a hybrid that worked but didn't feel complete. The electrons were still thought of as little particles traveling in definite paths, but with quantum restrictions imposed by hand, by assumption, without a deeper explanation for why those restrictions existed. The real revolution came in the 1920s, when several brilliant minds, working sometimes together and sometimes in parallel, developed a new and deeper theory, a true quantum mechanics that was stranger and more complete than anything that had come before. One of these people was a young Frenchman named Louis de Broglie, and he had a wild idea. If light, which everyone had thought was a wave, could behave like a particle, then maybe matter, which everyone thought was made of particles, could behave like a wave. Maybe electrons weren't just little balls orbiting a nucleus. Maybe they were also waves, ripples in some deeper quantum field, and maybe the allowed orbits in Bohr's atom were simply the orbits where these waves fit perfectly around the nucleus, resonating like the notes of a plucked string. A string on a musical instrument can only vibrate at certain frequencies, certain notes, because it's fixed at both ends, and only certain patterns of waves fit properly between those fixed points. De Broglie suggested that something similar happened with electrons in atoms. Only certain wavelengths fit properly around the nucleus, and these corresponded to Bohr's allowed orbits. It was a beautiful idea, and it turned out to be deeply true. You don't need to visualize this perfectly. You don't need to see the waves in your mind's eye. Just know that underneath the solidity of things, there's something rippling, something that's neither quite a wave nor quite a particle, but something that partakes of both natures, something fluid and strange. Soon after de Broglie's proposal, experimental physicists found direct evidence that electrons really do behave like waves. When they fired beams of electrons at crystals, the electrons created interference patterns just like light does in the double-slit experiment. Matter waves were real. But if electrons were waves, what exactly was waving? What was the medium? In water waves, it's water that goes up and down. In sound waves, it's air pressure that oscillates. But what about an electron wave? A young Austrian physicist named Erwin Schrödinger developed an equation, now called Schrödinger's equation, that described how these matter waves evolved over time. But the thing doing the waving, the thing his equation described, wasn't a physical substance like water or air. It was something more abstract, something that came to be called the wave function, usually written with the Greek letter psi. The wave function is a mathematical object that contains, in some sense, all the information about a quantum system. For a single particle, the wave function is spread out in space, and it changes and flows according to Schrödinger's equation. But what does it mean? What is it actually telling us? This question led to long arguments, debates that in some ways continue even now, nearly a century later. The most common answer, the interpretation that most physicists learned and used, came primarily from Max Born, and Niels Bohr and others working in Copenhagen in the 1920s. This interpretation says that the wave function doesn't tell you where a particle is. Instead, it tells you the probability of finding the particle in different places if you look for it, if you measure its position. The wave function, in this view, describes not reality itself but our knowledge about reality, or perhaps better, the potential for reality to crystallize into one definite outcome when we observe it. Before you measure the particle's position, it doesn't have a position, not in the usual sense. It's spread out, described by this rippling wave function. When you measure it, when you look, the wave function collapses, and suddenly the particle is here or there, in one definite spot, with probabilities given by the wave function's shape. This might sound strange, and it is strange, and it bothered many people, including Einstein, who famously said that God does not play dice with the universe. But the theory worked, with extraordinary precision, explaining everything from the structure of atoms to the behavior of light, from the chemistry that lets your body function to the semiconductors in electronic devices. Let yourself rest in the strangeness for a moment. You don't need to reconcile it or make it comfortable. The universe is strange, and that's all right. You're part of that strangeness, made of the same quantum stuff, and you've been existing just fine without understanding any of this, and you'll go on existing just fine whether you understand it or not. Another physicist, Werner Heisenberg, discovered something else, something that's woven into the very fabric of quantum mechanics. He found that there are certain pairs of properties that you simply cannot measure with perfect precision at the same time. The most famous example is position and momentum. Momentum is just mass times velocity, a measure of how fast something is moving and in what direction. Heisenberg showed that the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This isn't because our measuring instruments are clumsy. It's not that we just need better microscopes. It's a fundamental limit built into the nature of reality itself. The uncertainty is woven into the wave function, into the wave nature of matter. Think about it this way. A wave that's very spread out, stretching across a large region of space, has a well-defined wavelength. You can measure its oscillations clearly, but such a spread-out wave doesn't correspond to a particle being in any particular place. Conversely, if you want to pin down a particle's position, you need a wave function that's very concentrated, bunched up in a small region. But to create such a concentrated wave packet, you need to combine many different wavelengths together, which means the momentum becomes uncertain. This is called Heisenberg's uncertainty principle, and it applies not just to position and momentum, but to other pairs of properties as well. Energy and time form another such pair. If an event happens in a very short time, its energy becomes uncertain. If you want to measure energy precisely, you need to observe the system for a longer time. These aren't just abstract ideas. They have real consequences. The uncertainty principle is why atoms are stable, why electrons don't simply fall into the nucleus. If an electron were to sit exactly at the nucleus, its position would be known very precisely, which by the uncertainty principle would mean its momentum would be wildly uncertain, giving it enormous kinetic energy, enough to fling it far away from the nucleus. The electron settles into a kind of compromise, a lowest energy state where its position and momentum are both somewhat uncertain, creating a stable orbit, or rather, a stable cloud of probability around the nucleus. You can picture an atom, if you like, not as a tiny solar system, but as a fuzzy cloud, a region where there's a good chance of finding an electron if you look, with a tiny dense nucleus at the center. The cloud doesn't have sharp edges. It fades gradually, becoming less and less likely as you move farther out, but never quite reaching zero. In principle, there's a tiny probability that an electron in an atom in your body is, at this very moment, on the other side of the room, though that probability is so small that you'd need to wait far longer than the age of the universe to ever observe it happening. As physicists explored quantum mechanics more deeply, they discovered more and more strangeness, more ways in which the quantum world violated our everyday intuitions that were built by interacting with objects much larger than atoms, objects where quantum effects average out and become invisible. One of the strangest features is something called superposition. A quantum system can exist in a combination of multiple states at once, a kind of blurred, overlapping existence. An electron can be in a superposition of being in two places, or spinning in two directions, or having two different energies all at once, until you measure it, at which point it becomes definitely one thing or another. This leads to genuinely bizarre situations, paradoxes that seem to challenge logic itself. Schrödinger, who had developed the central equation of quantum mechanics, illustrated this with a thought experiment, a kind of dark joke involving a cat in a sealed box. The setup involves a quantum event, like a radioactive atom that has a 50% chance of decaying within an hour, connected to a mechanism that would kill the cat if the decay happened. According to quantum mechanics, until you open the box and look, The atom is in a superposition of having decayed and not decayed. And if the atom is in a superposition, then so is the entire apparatus, and so is the cat. The cat is, in some sense, both alive and dead at the same time, until you open the box, at which point the superposition collapses and the cat becomes definitely one or the other. Schrödinger meant this as a kind of reductio ad absurdum, showing that there was something wrong or incomplete about the theory if it led to such silly conclusions. But the universe, as it turns out, doesn't care about what seems silly to us. Quantum superposition is real, and it happens all the time at the scale of atoms and photons. The question of why we don't see it at larger scales, why cats and people seem to be definitely one way or another rather than in blurred superpositions, is part of what's called the measurement problem, and it's something that physicists and philosophers are still working through. One possible answer is that large objects are constantly interacting with their environments, with air molecules and photons and all sorts of things, and these interactions cause superpositions to collapse very quickly, almost instantly, through a process called decoherence. The quantum weirdness is still there, but it gets scrambled and lost in the noise, hidden away so that the world appears classical, appears normal to us. You might be feeling very relaxed now. And if your thoughts are drifting away from quantum mechanics towards sleep or dreams, that's exactly right. There's no test later, no quiz, no reason to stay alert. The quantum world will keep doing its strange dance whether you're paying attention or not. There's another quantum phenomenon, perhaps even stranger than superposition, called entanglement. It happens when two or more particles interact in such a way that their wave functions become intertwined, connected, so that you can't describe one particle's state without referring to the other's state. Imagine you have two particles, perhaps two photons, created together in a special way so that they're entangled. You send one photon to one side of a laboratory and the other photon to the opposite side, far apart. Quantum mechanics says that if you measure certain properties of one photon, you'll instantly know the corresponding property of the other photon, even though they're separated by a large distance, and even though neither photon had a definite value for that property before you measured it. Einstein called this spooky action at a distance, and he thought it revealed a flaw in quantum mechanics. He believed that the particles must have carried hidden information with them, predetermined values for all their properties, like secret instructions, so that the correlation you see when you measure them isn't really mysterious at all, just a matter of uncovering information that was already there. But in the 1960s, a physicist named John Bell showed how to test this idea. He derived an inequality, a mathematical relationship that would have to hold if Einstein was right, if there were hidden variables determining everything in advance. And when experiments were done, testing Bell's inequality, they found that it was violated. Nature broke the inequality. The correlations were stronger than any hidden variable theory could explain. This means that entanglement is real, genuinely strange, and not just a matter of our ignorance. When you measure one particle of an entangled pair, something happens to the other particle, instantly, no matter how far apart they are. But this doesn't allow faster-than-light communication, because the results of measurements on one particle appear random until you compare them with the results from the other particle, and that comparison requires sending information through ordinary slower-than-light channels. Entanglement is now used in practical technologies, in quantum cryptography for secure communication, and it's a key resource in the development of quantum computers, which are machines that exploit superposition and entanglement to perform certain calculations far faster than ordinary computers ever could. It's worth pausing to think about how remarkable all of this is. The universe, at its smallest scales, doesn't work the way our senses tell us things should work. Particles don't have definite properties until we observe them. They can be in multiple states at once. They can be connected across vast distances. And yet, this strange, dreamlike behavior underlies everything. The chair you sit on, the light by which you read, your own thoughts, all of it emerges from this quantum foundation. For much of the 20th century, quantum mechanics was primarily concerned with understanding individual particles or small systems, atoms and molecules and light. But physicists also worked to extend quantum ideas to fields, to things like the electromagnetic field that fills space. This led to quantum field theory, a framework where particles themselves are understood as excitations, as little ripples or vibrations in underlying quantum fields. The electromagnetic field, when quantized, gives rise to photons. There are fields for electrons, fields for quarks, fields for all the fundamental particles we know about, and these fields exist everywhere, filling the universe, and particles are just places where the fields are excited, oscillating. In this picture, what we call empty space, the vacuum, isn't truly empty. It's full of fields in their lowest energy states, their ground states, and even in these ground states there are fluctuations, brief sparkles of energy where particles and antiparticles pop into existence for a moment, and then annihilate each other and disappear. These vacuum fluctuations are real and measurable. They cause tiny shifts in the energy levels of atoms, effects that have been detected with extraordinary precision. Quantum field theory, combined with what's known as the Standard Model of particle physics, explains almost everything we've ever observed about the behavior of matter and forces, from the interactions of quarks inside protons and neutrons to the way electrons and light interact, from radioactive decay to the Higgs boson, discovered in 2012. But there are still mysteries, still places where our understanding is incomplete. Gravity, the force that holds you to the Earth and holds planets in orbit around stars, is described by Einstein's general relativity, a beautiful theory where gravity is understood as the curvature of spacetime itself. But general relativity is not a quantum theory. It treats spacetime as smooth and continuous, and when physicists try to combine it with quantum mechanics to create a theory of quantum gravity, they run into deep mathematical problems, infinities that appear in the equations and can't be easily removed. There are many ideas for how to solve this, from string theory, which imagines that the fundamental constituents of reality are tiny vibrating strings rather than point particles, to loop quantum gravity, which suggests that spacetime itself is granular, made of discrete chunks at the smallest scales. But we don't yet know which, if any, of these approaches is correct. We don't yet have a complete theory of quantum gravity, a theory that would describe what happens inside black holes, or at the very first instant of the Big Bang. Let your mind wander through these ideas gently. Imagine fields rippling through empty space, particles winking in and out of existence, spacetime itself bending and perhaps even vibrating at scales too small to see. It's all happening right now, all around you, in the space between your atoms, in the light touching your skin. Throughout the history of quantum mechanics, people have asked what it all means. The mathematics works beautifully, predicting experimental results with incredible accuracy, but the interpretation, the question of what's really happening, has never been fully settled. The Copenhagen interpretation, the one that Bohr and his colleagues developed, says that quantum mechanics is complete, that the wave function is all there is, and that it's meaningless to ask what a particle is doing when you're not observing it. The act of measurement is fundamental, somehow bringing reality into being. But there are other interpretations. The many worlds interpretation, proposed by Hugh Everett in the 1950s, suggests that the wave function never collapses at all. Instead, every time a quantum measurement happens, every possible outcome actually occurs, but in different branches of reality. The universe splits, and in one branch you observe one result, and in another branch another version of you observes a different result, and both are equally real, existing in parallel. Then there's the pilot wave theory, also called de Broglie-Bohm theory, which brings back the idea of particles having definite positions at all times. In this view, particles ride along on waves, guided by them, and the randomness we observe comes from our ignorance of the particle's exact starting conditions, not from any fundamental indeterminacy. There are other interpretations too, and the remarkable thing is that they all make the same experimental predictions. They're different stories about the same mathematics, different ways of thinking about what's real, and we have no way, at least not yet, to experimentally distinguish between them. Maybe this tells us something important. Maybe the universe doesn't care how we choose to think about it, as long as the mathematics works. Or maybe we're missing something, some deeper insight that would make everything click into place and seem obvious in retrospect. Quantum mechanics has now been tested in countless ways, in experiments subtle and profound, from the microscopic to scales much larger than individual atoms. Physicists have created quantum superpositions of molecules with hundreds of atoms. They've demonstrated quantum entanglement across kilometers of distance, across cities, even between the Earth and satellites in orbit. Every test has confirmed what the theory predicts, down to astonishing levels of precision. And yet the theory still feels, to many people, incomplete or unsatisfying. Not because it makes wrong predictions, but because it challenges our intuitions about what reality is. We want to believe that things are definite, that particles are here or there, that effects follow causes in a clear sequence, that distant objects can't influence each other instantaneously. Quantum mechanics gently but firmly insists that these wants, these intuitions, are just habits of thought built from our experience with a narrow slice of reality, the classical world of middle-sized objects, and that the deeper reality is genuinely different, genuinely strange. Perhaps strangeness is all right. Perhaps the universe doesn't owe us familiarity or comfort. Perhaps it's enough that there are rules, deep mathematical structures that govern how things behave, even if those rules seem bizarre when translated into everyday language. You might think about what it means that you are made of quantum things, that every atom in your body is a little cloud of probability, that the electrons enabling your thoughts to happen right now are in superpositions, described by wave functions, existing in ways that defy simple description. And yet here you are, thinking, feeling, experiencing a world that seems solid and definite. Somewhere in the transition from the quantum to the classical, from atoms to cells to bodies to minds, the strangeness gets hidden. It doesn't go away, but it becomes invisible, averaged over, smoothed out by the sheer number of particles involved, by the constant interaction with the environment. You are a classical island in a quantum sea, or maybe you're a quantum system so complex that you trick yourself into feeling classical. The study of quantum mechanics also revealed something about the limits of knowledge itself. It's not just that we don't know certain things. It's that certain things cannot be known, even in principle. The uncertainty principle places a boundary on the precision of our knowledge, not because of technological limitations, but because of the structure of reality. And the measurement problem. The question of what happens when we observe a quantum system suggests that observation itself plays a strange role in the universe, that the line between observer and observed is blurry in ways we still don't fully understand. Some people have taken these ideas in philosophical or even mystical directions, suggesting that consciousness creates reality, or that quantum mechanics validates ancient spiritual teachings. Most physicists are skeptical of such claims. The role of measurement in quantum mechanics doesn't necessarily have anything to do with consciousness. A detector, a machine, can collapse a wave function just as well as a person can. The mystery is about the physical process of interaction, not about minds or awareness. But it's true that quantum mechanics invites philosophical reflection. It asks us to think carefully about what we mean by existence, by reality, by knowledge. It doesn't provide easy answers, but it sharpens the questions. As you lie here, relaxing, breathing slowly, you're participating in one of the great mysteries. Air molecules, quantum particles, are flowing in and out of your lungs. Photons are striking your retinas if your eyes are open, or the darkness itself is a kind of quantum state if they're closed. Chemical reactions driven by quantum mechanics, by the behavior of electrons in atoms and molecules, are powering your cells, keeping you alive. All the complexity of life, the intricate machinery of biology, rests on a foundation of quantum rules. The way DNA molecules hold their structure, the way enzymes catalyze reactions, the way plants capture sunlight and turn it into energy, all of this depends on quantum mechanics working exactly as it does. In some biochemical processes, quantum effects might even play an active role beyond just setting the rules for how atoms bond. There's evidence that photosynthesis, the process by which plants convert light into chemical energy, might exploit quantum coherence, maintaining quantum superpositions for brief moments to search more efficiently for pathways to transfer energy. Birds might use quantum entanglement in their eyes to sense the Earth's magnetic field and navigate during migration. These are areas of active research, places where quantum mechanics meets biology in surprising ways. Time itself has a strange relationship with quantum mechanics. In the classical world, time flows smoothly, carrying us from past to future. But in quantum mechanics, the Schrödinger equation treats time very differently from space. Time is a parameter, something external, something the wave function evolves through, while space is part of what the wave function describes. When you combine quantum mechanics with relativity, things get even stranger. Relativity tells us that time is relative, that different observers can disagree about the order of events, that time and space are woven together into spacetime. Quantum field theory manages to incorporate some of this, treating particles as excitations in relativistic quantum fields, but the full marriage of quantum mechanics and gravity, the complete unification of the very small and the very large, remains elusive. At the Planck scale, a distance so small that it's hard to even imagine, about 10 to the power of negative 35 meters, and a time so brief, about 10 to the power of negative 44 seconds, quantum fluctuations of spacetime itself should become important. At this scale, the smooth geometry of spacetime that general relativity describes should break down into a quantum foam, a seething, fluctuating structure that we have no direct way to observe and no complete theory to describe. And yet the universe came from something like this, if the Big Bang theory is correct. In the first tiny fraction of a second after the universe began, everything we see now, all the galaxies and stars and planets, all the matter and energy was compressed into a region smaller than an atom, and quantum effects dominated. The patterns we see in the cosmic microwave background, the faint afterglow of the Big Bang, are thought to originate from quantum fluctuations in that early universe, tiny ripples that got stretched and amplified as space expanded, eventually becoming the seeds from which galaxies formed. So quantum mechanics isn't just about the small. In a sense, it's about the largest structures in the universe too, about the origin and evolution of everything. You're floating now, perhaps, in the space between waking and sleeping, and these ideas are floating with you, images of waves and particles, probabilities and uncertainties, fields and fluctuations. You don't need to hold on to any of it. You can let it all drift away, knowing that the universe is vast and strange, and that your place in it is both infinitesimally small and infinitely precious. One of the beautiful things about quantum mechanics is how it connects everything. All electrons are identical, fundamentally indistinguishable from each other. The electron in your body is the same, in every meaningful way, as an electron in a star on the other side of the galaxy. They're not just similar, they're identical, perfect copies, or perhaps better, they're all the same thing, excitations of the same underlying electron field. This means there's a kind of unity to matter, a sameness beneath the diversity. Everything is made of the same quantum building blocks, following the same quantum rules, and this has been true since the beginning. Quantum mechanics also gives us a new perspective on what's possible and what's not. In the classical world, if something is forbidden by energy conservation, it simply can't happen. But in the quantum world, the uncertainty principle allows brief violations of energy conservation, as long as they're brief enough. A particle can borrow energy from the vacuum, pop into existence where it shouldn't be able to exist, as long as it pays the energy back quickly enough that the uncertainty principle is satisfied. This allows for processes called quantum tunneling, where particles pass through barriers that they don't have enough energy to climb over. They tunnel through, using the strangeness of quantum mechanics to do something that would be impossible classically. Tunneling is crucial for many things. It's how alpha particles escape from radioactive nuclei. It's how the sun generates energy, because protons in the sun's core can tunnel through the electrical repulsion barrier and fuse together, releasing energy in the process. Without quantum tunneling, the sun wouldn't shine, and we wouldn't be here. It's also how some electronic devices work, and it might even be how some enzymes in your body work, speeding up chemical reactions by allowing atoms to tunnel through energy barriers, taking shortcuts that classical chemistry wouldn't permit. The idea of tunneling captures something essential about the quantum world. Nothing is absolutely forbidden, only more or less probable. Barriers are not walls but obstacles that can sometimes be passed through, and the distinction between possible and impossible becomes softer, more graduated, expressed in probabilities rather than absolutes. You can rest in this softness, in this gradualness. The universe is not harsh in its boundaries. It allows for flexibility, for fluctuation, for brief transgressions that return to equilibrium. There's a gentleness in the way quantum mechanics works, even in its strangeness, Let's think about atoms again, but more slowly this time, with more detail. An atom is mostly empty space. If you imagine the nucleus as a grain of sand in the center of a football field, the electrons would be like tiny specks somewhere out near the stands, and all the space in between would be empty, or what seems like empty, though we know now that it's filled with quantum fields. The nucleus itself is made of protons and neutrons, and these in turn are made of quarks, fundamental particles that come in different varieties called flavors, with whimsical names like up and down, strange and charm. Quarks are bound together by the strong nuclear force, one of the 4 fundamental forces in nature, mediated by particles called gluons. The strong force is remarkable because it gets stronger as you try to pull quarks apart, unlike gravity or electromagnetism, which get weaker with distance. Try to separate 2 quarks, and the force between them increases until you've put in enough energy that you create new quarks from the vacuum, and you end up with 2 bound pairs instead of 2 free quarks. This is why we never see individual quarks in isolation, only bound together in groups. The other forces are electromagnetism, which we've talked about, the weak nuclear force, which is responsible for certain kinds of radioactive decay, and gravity, which we experience every moment but which is by far the weakest of the 4 forces at the scale of particles. All of these forces, except gravity, are described by quantum field theory, by the Standard Model, which is one of the most successful scientific theories ever developed. It makes predictions that have been tested to extraordinary precision, sometimes agreeing with experiment to 10 decimal places or more. And yet physicists know the Standard Model is incomplete. It doesn't include gravity. It doesn't explain dark matter, the invisible substance that makes up most of the matter in the universe. It doesn't explain dark energy, the mysterious force that's causing the universe's expansion to accelerate. It doesn't explain why there's more matter than antimatter, why the universe didn't just annihilate itself in the first moments after the Big Bang. These are puzzles for the future, questions that the next generation of physicists will work on, perhaps discovering new particles, new forces, new principles that will expand our understanding even further. But even with its incompleteness, quantum mechanics, and the theories built on it, have given us a picture of reality that's richer and stranger than anyone imagined a century ago. We live in a universe where particles can be in multiple places at once, where empty space seethes with energy, where distant objects can be connected in ways that transcend space, where the act of observation plays a fundamental role in determining what happens. It's worth reflecting on how counterintuitive this all is. Nothing in your daily experience prepares you for quantum mechanics. You've never seen a person in 2 places at once. You've never observed an object tunneling through a wall. The world appears solid, definite, comprehensible. This is because quantum effects are incredibly fragile. They're easily destroyed by interaction with the environment, a process we mentioned before called decoherence. When a quantum system, a particle in a superposition of states, interacts with the environment, with air molecules or photons or any of the countless particles around it, the superposition gets entangled with the environment's degrees of freedom, and very quickly the quantum coherence is lost, scrambled into the environment in a way that's effectively irreversible. This is why quantum computers are so difficult to build. They need to maintain quantum superpositions and entanglement, long enough to perform calculations, but any interaction with the environment causes decoherence, causing errors. Building a quantum computer requires isolating the quantum bits, the qubits, from the environment as much as possible, keeping them at temperatures close to absolute zero, shielding them from stray electromagnetic fields, and even then, the coherence times are limited. But progress is being made. Quantum computers with dozens or hundreds of qubits now exist, and while they're not yet powerful enough to outperform classical computers on most tasks, there are specific problems where they show promise. Simulating quantum systems, for instance, is something quantum computers should be naturally good at, since they themselves are quantum systems. In the future, quantum computers might help us design new materials, new medicines, by simulating the quantum mechanics of molecules far more efficiently than classical computers can. They might break current encryption systems, which is why researchers are also working on quantum-resistant cryptography. They might solve optimization problems in logistics, finance, artificial intelligence, or they might remain niche tools, useful for certain specialized tasks but not revolutionary. It's hard to predict. Technology often surprises us, taking paths we don't expect. But whether or not quantum computers change the world, the principles underlying them, the principles of quantum mechanics, have already changed the world in countless ways. The transistor, the basic building block of all modern electronics, relies on quantum mechanics. The laser, used in everything from barcode scanners to surgery to fiber optic communication, is a fundamentally quantum device, producing light where all the photons are in the same quantum state, coherent with each other. MRI machines, which let doctors see inside your body without surgery, work because of quantum mechanics, because atomic nuclei have a property called spin, a quantum property that makes them behave like tiny magnets, and these magnetic moments can be manipulated and detected using magnetic fields and radio waves. Even something as everyday as the color of objects, the reason the sky is blue and leaves are green, comes down to quantum mechanics, to the way electrons in atoms and molecules absorb and emit photons of specific energies, specific wavelengths. You're surrounded by quantum technology, by devices that wouldn't work if quantum mechanics weren't true, and you're made of quantum processes, cells running on molecular machines that exploit quantum rules, and the light by which you see is itself quantum, made of photons, and the solidity you feel when you touch something is the result of quantum forces, electrons in your hand repelling electrons in the object through electromagnetic interactions. Everything is quantum beneath the surface. The classical world is an approximation, a useful fiction that emerges when quantum systems become large and complex enough. There's something almost dreamlike about this, the idea that the world you experience is a kind of veil over something stranger, something that doesn't quite make sense in ordinary terms, but that follows deep mathematical laws. And perhaps dreams themselves are related in a distant way to quantum mechanics, because your brain is a physical system, neurons firing in patterns that ultimately depend on quantum processes, molecules changing shape, ions flowing through channels, and somewhere in that complexity, consciousness arises, awareness, the experience of being you. We don't understand consciousness, not really. We don't know how subjective experience emerges from physical processes. Some people have speculated that quantum mechanics might play a role, that something about quantum superposition or entanglement might be necessary for consciousness. But these ideas are controversial and speculative, without clear evidence. What is clear is that you don't need to understand quantum mechanics to experience consciousness, to think and feel and dream. The universe arranged itself, through billions of years of cosmic and biological evolution, to create structures complex enough to contemplate their own existence, to wonder about the nature of reality, and that's remarkable regardless of the details. Let's return to the idea of fields, because it's such a central concept in modern physics, and it's worth exploring more slowly. A field is something that has a value at every point in space. The temperature in a room is a field, warmer near the heater, cooler near the window, with a specific temperature at every location. The gravitational field around Earth is a field, stronger at the surface, weaker as you go higher, determining how objects fall and orbit. In quantum field theory, every type of particle is associated with a field that fills all of space. The electron field exists everywhere, and what we call an electron is a localized excitation of that field, a ripple, a quantum of the field's energy. Similarly for all the other particles. This perspective dissolves the distinction between matter and energy in a deep way. E equals mc squared, Einstein's famous equation, tells us that mass and energy are equivalent, convertible into each other. But in quantum field theory, particles themselves are just forms of energy, vibrations in fields, and when a particle and its antiparticle meet and annihilate, they don't really disappear. They transform into other particles, photons perhaps, different vibrations in different fields. The vacuum, the state where no particles are present, is the ground state of all these fields. But as we've mentioned, even the ground state has energy, has fluctuations. The fields are never perfectly still. They're always quivering, and occasionally these quiverings can become strong enough to create real particles, virtual particles popping into existence and then disappearing. This vacuum energy has consequences. It creates a tiny force between two metal plates placed very close together in a vacuum, called the Casimir effect. The plates restrict which vacuum fluctuations can exist between them, creating a difference in energy density that pushes the plates together. This has been measured experimentally, a direct demonstration that the quantum vacuum is not empty. Some physicists have speculated that vacuum energy, if it exists throughout the universe, might be related to dark energy, the mysterious force causing the universe to expand faster and faster, but the numbers don't match. When you try to calculate how much vacuum energy there should be, you get an answer that's enormously larger than what we observe, one of the biggest unsolved problems in physics. This is sometimes called the cosmological constant problem, and it suggests that there's something fundamental we don't understand about the relationship between quantum mechanics and gravity, between the very small and the very large. The universe is full of such puzzles, places where our understanding reaches a boundary and we can see questions but not yet answers. And that's all right. Science is not a collection of finished knowledge but an ongoing process, a conversation between observation and theory, experiment and mathematics, that's been going on for centuries and will continue long into the future. You're part of this universe, this great unfolding mystery, and you carry the same fundamental nature as stars and galaxies, atoms and photons. You're made of particles that were forged in the cores of ancient stars, stars that lived and died billions of years ago. And those particles are following quantum rules, the same rules they've always followed, dancing in patterns that create the temporary structure you call your body, your life. There's a concept in quantum mechanics called quantum state, which is the complete description of a system. For a single particle, the quantum state is given by the wave function. For multiple particles, the state becomes more complex, existing in a higher dimensional space where each particle's possible positions and properties are represented. When particles are entangled, their quantum state can't be separated into individual states for each particle. The whole is genuinely more than the sum of its parts. The state describes the system as an irreducible whole, and measuring one particle affects the entire state, instantaneously changing what you'd predict for the other particles, no matter how far away they are. This holistic nature of quantum states has led some people to see connections between quantum mechanics and Eastern philosophies, which often emphasize the interconnectedness of all things, the idea that separation is an illusion, and that everything is part of a greater whole. Whether such connections are meaningful or superficial is debatable. Quantum mechanics is a mathematical theory about the behavior of matter and energy. It doesn't make claims about consciousness or spirituality or the meaning of life, but it does reveal that reality is more interconnected, more relational, less divided into separate independent objects than classical physics suggested. Perhaps this is enough. Perhaps knowing that you're connected to everything else through the quantum fields that fill space, that the particles making you were once part of stars and will someday be part of something else. Perhaps this provides a kind of comfort, a sense of belonging to something larger. The mathematics of quantum mechanics can be beautiful, even if you don't follow all the details. The Schrödinger equation, the central equation describing how quantum states evolve, has an elegance to it, a simplicity in its form that belies the complexity of its solutions. It's a linear equation, which means that if you have two solutions, any combination of them is also a solution. This is what allows for superposition, for the adding together of different quantum states. There's also the Heisenberg formulation of quantum mechanics, which looks quite different from Schrödinger's approach but is mathematically equivalent. In Heisenberg's picture, the quantum states stay still, and the observables, the things you might measure like position or momentum, evolve in time. It's like watching a play where the stage rotates but the actors stand still, versus watching the actors move while the stage stays fixed. Different perspectives on the same underlying reality. And there's the path integral formulation, developed by Richard Feynman, which imagines that a particle going from one place to another doesn't follow a single path, but instead takes all possible paths simultaneously. and you calculate the probability of getting from here to there by adding up contributions from every path, with each path having a certain quantum phase, and the phases interfere with each other constructively and destructively to give the final result. This might sound insane, the idea that a particle somehow explores every possible trajectory, but it's an incredibly powerful way to do calculations, and it provides deep insights into the nature of quantum mechanics, revealing connections to classical physics, to the principle of least action, which says that classical systems follow the path that minimizes a certain quantity called action. In the quantum version, all paths contribute, but the paths near the classical path tend to have similar phases and add up constructively, while paths far from the classical path have rapidly varying phases and tend to cancel out, which is why large objects appear to follow definite classical trajectories, even though quantum mechanically they're exploring all possibilities. You don't need to visualize this perfectly or understand the mathematics. Just know that there are multiple ways of thinking about quantum mechanics, multiple mathematical formulations that are all equivalent, all describing the same physical reality from different angles, and physicists choose whichever formulation makes a particular problem easiest to solve. This multiplicity of perspectives is characteristic of deep truths. Something real and fundamental can be approached from many directions, described in many languages, and each description reveals different aspects, different facets of the same underlying thing. Let's think about time again more carefully. In everyday life, time seems to flow, carrying us from past to future, and the past feels different from the future. We remember the past but not the future. Eggs break but don't unbreak. Coffee cools but doesn't spontaneously heat up. There's an arrow to time, a directionality. But the fundamental laws of physics, both classical and quantum, are time-symmetric. If you watch a movie of particles bouncing around, you can't tell if it's playing forward or backward. The equations work the same either way. So where does the arrow of time come from? The answer has to do with entropy, a measure of disorder, and the second law of thermodynamics, which says that entropy tends to increase. A broken egg has higher entropy than an intact one. More disorder, more ways the molecules can be arranged while still looking broken. The universe, it seems, started in a very low entropy state, very ordered at the Big Bang, and has been becoming more disordered ever since. This gives time its arrow. We remember the past because memories are physical records, low entropy structures in our brains, and creating such structures requires increasing entropy elsewhere, in accordance with the second law. We can't remember the future because we can't create records of things that haven't happened yet. Quantum mechanics doesn't change this basic picture, but it adds subtleties. The time evolution of a quantum state, according to the Schrödinger equation, is reversible, symmetric in time. But the act of measurement, the collapse of the wave function, seems to introduce irreversibility, seems to create an arrow of time. Some interpretations of quantum mechanics, like the many-worlds interpretation, avoid wave function collapse entirely, and thus preserve time symmetry. In that view, entropy increase and the arrow of time come purely from our perspective, from the fact that we're embedded in one branch of the wave function and see the other branches as increasingly inaccessible, forgotten by decoherence. These are deep questions, still being explored, still being debated. The relationship between quantum mechanics, thermodynamics, and the nature of time is subtle and not fully understood. But for you, right now, time is simply passing, gently, carrying you toward sleep, and the past few minutes or hours are already fading into memory, and the future is unknown, and the present moment is all there really is, the only place where you actually exist, and in this present moment you can rest, you can let go, knowing that the universe will continue its quantum dance whether you're awake to think about it or not. The word quantum itself comes from Latin, meaning how much related to quantity. It captures the essence of the quantum revolution, the discovery that things come in discrete amounts, in chunks, rather than being infinitely divisible. You can't have half a photon or a third of an electron. These things come in indivisible units, quanta, and this granularity is woven into the fabric of reality at the smallest scales. But there's a paradox here, because the wave function itself is continuous. It can have any value, smoothly varying across space. It's when you measure something, when you detect a particle or determine its energy, that you find discrete outcomes, quantized values. So quantum mechanics is neither fully continuous nor fully discrete. It's both or something else entirely, something that transcends this dichotomy. This is part of why quantum mechanics resists easy visualization or simple explanation. It doesn't fit neatly into the categories our language and intuition provide. We're forced to use mathematics, to use equations and probabilities, to capture what's happening. And even then, the interpretation remains open to debate. Perhaps this is fitting. Perhaps reality at its deepest level is not something that can be fully captured in words or pictures, only in symbols and relationships, patterns and equations. Mathematics itself is mysterious when you think about it. Why should abstract patterns in our minds correspond so precisely to the behavior of the physical world? Why should equations predict the outcomes of experiments, sometimes decades before the experiments can be performed? Eugene Wigner, a physicist and mathematician, called this the unreasonable effectiveness of mathematics in the natural sciences. It's as if the universe is mathematical, or as if mathematics and physical reality are two aspects of the same thing, and this is strange and wonderful and perhaps ultimately inexplicable. But it works. The equations of quantum mechanics, despite their abstraction, predict what happens when you do experiments again and again with extraordinary accuracy. This is why physicists trust the theory, even when it seems strange. It's not a matter of faith or preference, but of evidence, of countless experiments that could have contradicted the theory but didn't, and this predictive power has been used to build technologies, to create devices that wouldn't work if quantum mechanics were wrong. So quantum mechanics is not just a theory, not just an idea. It's a tested, reliable description of how nature behaves, as well established as any scientific knowledge we have. Let your breathing slow, in and out, gentle and easy. Feel the weight of your body wherever you are, supported and safe. The quantum world is always there, underlying everything, but you don't need to think about it. You can simply be, simply exist, as you always have, as all things always have. There's a principle in quantum mechanics called complementarity, introduced by Niels Bohr. It says that different experimental arrangements reveal different, complementary aspects of quantum systems. Whether light behaves as a wave or a particle depends on how you observe it, on what question you ask. In one experiment, the double-slit experiment we mentioned earlier, light shows its wave nature, creating interference patterns. In another experiment, like the photoelectric effect, light shows its particle nature, delivering energy in discrete packets. Both descriptions are valid, but they apply to different situations, different contexts. This led Bohr to a philosophical position where he argued that we can't speak meaningfully about what a quantum system is doing independent of how we observe it. The properties of a system are not intrinsic but relational, defined by the interaction between the system and the measuring apparatus. This was controversial, and it remains controversial. Einstein, among others, believed there should be an objective reality independent of observation, that particles have definite properties even when we're not looking. But experiment after experiment has sided with Bohr, or at least with the predictions of quantum mechanics that incorporate this relational contextual view. The universe, it seems, does not have definite properties waiting to be discovered. It has potentialities that crystallize into actualities through interaction and measurement. This is a profound shift from the classical worldview, where objects were thought to have definite properties at all times, independent of observation. In the quantum view, properties are not possessed but manifested, brought into being through the act of observation. You might think of it like this. Imagine a word in a language you don't know. The word has potential meanings, but those meanings only become actual when the word is used in a sentence, in a context, in relation to other words. The meaning is not sitting inside the word waiting to be extracted. It emerges from relationships, from context. Quantum properties are similar. They're not sitting inside particles waiting to be measured. They emerge from the relationship between the particle and the measuring device, from the context of the experiment. This might feel uncomfortable, this lack of definite underlying reality, and that's understandable. We're used to thinking of the world as made of things with properties, objects that exist in specific states whether we look at them or not. But the universe doesn't have to conform to our comfort or our intuitions. It is what it is, and quantum mechanics describes what it is with remarkable accuracy, even if the description is strange. There's a beauty in accepting this strangeness, in letting go of the need for reality to be simple or familiar. The universe is under no obligation to make sense to us, and yet we can still understand it, mathematically, experimentally, even if that understanding doesn't translate into a comfortable mental picture. Over the decades since quantum mechanics was developed, physicists have found quantum behavior in more and more systems, at larger and larger scales. Superconductors, materials that conduct electricity with zero resistance when cooled to very low temperatures, are macroscopic quantum systems, where electrons pair up and move together in a coordinated quantum state extending across the entire material. Superfluids, like liquid helium, cool below a certain temperature, flow without friction, climb up the walls of containers, behave in ways that are completely alien to our everyday experience of fluids. These are also macroscopic quantum phenomena, where quantum mechanics governs the collective behavior of enormous numbers of atoms. Bose-Einstein condensates, created in laboratories by cooling gases to temperatures just billionths of a degree above absolute zero, are states of matter where thousands or millions of atoms all occupy the same quantum state, becoming indistinguishable, behaving as a single quantum entity. These exotic states of matter show that quantum mechanics is not just about individual particles but about collective phenomena, emergent behaviors that arise when many quantum systems interact. And all of these discoveries, all of these strange states of matter, follow from the same basic principles we've been discussing: the wave-particle duality, the uncertainty principle, the quantization of energy, the wave function, and its evolution. The principles are simple, in a sense, or at least they can be stated simply, but their consequences are vast, extending into every corner of physics, chemistry, materials, science, biology. You're lying here, resting, and the materials around you, the mattress, the sheets, whatever you're touching, are all in quantum states, vast ensembles of atoms each described by wave functions, all interacting through quantum forces. And the overall behavior, the classical solidity and stability you experience, emerges from this quantum foundation. It's turtles all the way down, as the old joke goes, but in this case, it's quantum mechanics all the way down. And then, perhaps, something even deeper that we haven't discovered yet, some theory that unifies quantum mechanics and gravity, some final theory of everything, or perhaps there is no final theory, only deeper and deeper levels of description, mysteries beneath mysteries, forever. In some ways, quantum mechanics has made the universe more mysterious, not less. Before quantum mechanics, it seemed possible that we might eventually understand everything, that we might find simple laws that explained all phenomena, and then science would be complete. But quantum mechanics revealed that nature is irreducibly probabilistic, that there are limits to what can be known, that observation plays a strange and essential role, and these revelations opened up new questions, philosophical questions about the nature of reality, about what exists and what it means to exist. And the more we've learned, the more we've discovered how much we don't know. Dark matter, dark energy, the origin of mass, the hierarchy problem, the strong CP problem, the cosmological constant problem, all of these puzzles suggest that the standard model in quantum mechanics, despite their success, are not the end of the story. There are hints of deeper structures, symmetries, principles waiting to be discovered. String theory, with its extra dimensions and vibrating strings, is one attempt to find those deeper structures. Loop quantum gravity, supersymmetry, other approaches are also being explored. Or maybe the answer is something no one has thought of yet. Some radical new idea that will make everything clear in retrospect. The way quantum mechanics itself must have seemed radical and strange when it was first proposed but now seems inevitable, the only way things could be. The history of physics is a history of revolutions, of overturning previous understanding, and there's no reason to think we've reached the end of that process. Future generations will probably look back at our current theories the way we look back at Newton's mechanics, as a good approximation, accurate in certain regimes, but incomplete, missing something essential. And that's exciting in a way. It means there's still so much to discover, so much we don't know, mysteries waiting to be unraveled by people not yet born, questions not yet asked. But for now, for tonight, you can rest in the knowledge we have, partial and provisional though it may be. You can know that the universe follows rules, deep mathematical rules, and that we've uncovered some of those rules, enough to make sense of atoms and molecules, light and matter, stars and galaxies. You can know that you're part of this vast cosmos, made of the same stuff, following the same laws, connected to everything through the quantum fields that fill space. And you can let all of this fade into the background, let your thoughts drift into sleep, into dreams, where perhaps quantum superpositions of neural states create narratives that never quite make sense, where the normal rules are suspended, and anything seems possible. Sleep itself is a quantum process, in the sense that it emerges from the quantum mechanics of neurons and neurotransmitters, molecules changing shape, ions flowing, electrical signals propagating. But it's also much more than that, much more than the sum of its quantum parts. Consciousness, awareness, the subjective experience of being you, these emerge from quantum mechanics but transcend it, become something new, something qualitatively different from particles and fields. This is emergence, the way complex systems can have properties that aren't present in their individual components. Water molecules aren't wet, but a collection of them creates wetness. Neurons aren't conscious, but a network of them creates consciousness, or at least correlates with it in ways we're still trying to understand. Quantum mechanics provides the foundation, the basic rules, but it doesn't explain everything. There are higher levels of organization, emergent phenomena, that require their own descriptions, their own principles. And perhaps this is how the universe works at every level. Each scale has its own appropriate description, its own effective theories, and while deeper levels constrain what's possible at higher levels, they don't fully determine it. There's novelty at each level, new patterns, new behaviors, new kinds of complexity. You are one such complexity, a pattern of matter and energy organized in a very particular way, stable enough to persist for decades, complex enough to think and feel and wonder, temporary enough that someday you'll dissolve back into simpler forms, the atoms that make you scattering and becoming parts of other things, other patterns. But for now, you're here, you're you, a local decrease in entropy, a temporary island of order in an ocean of increasing disorder. And that's enough. That's everything. The quantum world beneath your experience is doing its dance, particles and fields fluctuating, interacting, creating the stability that lets you exist, and you don't need to understand it or think about it for it to work. It's been working since before you were born, since before the Earth formed, since the beginning of the universe, and it will continue working long after you're gone, the same quantum rules playing out in new configurations, new patterns, endlessly creative, endlessly surprising. There's a term in quantum mechanics called ground state, the lowest energy state of a system, the state a system settles into when left alone, when allowed to relax completely. Atoms have ground states. Molecules have ground states. Even the vacuum, empty space, is the ground state of all the quantum fields. Perhaps sleep is like a ground state for consciousness, the configuration your brain settles into when released from the demands of waking life, when allowed to relax, to let go. And perhaps this moment, right now, as you drift between waking and sleeping, is a kind of transition state, a superposition of awake and asleep, consciousness and unconsciousness, and soon the wave function will collapse into one outcome or the other, and you'll find yourself fully in the dream state, or fully awake, and either is fine, either is part of the natural rhythm of things. Quantum mechanics tells us that transitions between states happen, that energy levels change, that nothing stays the same forever. Everything fluctuates. Everything evolves, following the equations, following the deep mathematical patterns that govern all of reality. And these patterns, these quantum rules, are the same everywhere in the universe, as far as we can tell. The atoms in distant galaxies behave the same way as atoms here on Earth. The light from stars billions of light years away shows the same absorption lines, the same quantum transitions, as light from our sun. This universality is remarkable. The laws of physics don't change from place to place, from time to time. They're constant, reliable, the same today as they were billions of years ago, the same here as they are in the most distant galaxy we can see. This gives us confidence that what we learn from experiments here, and now applies everywhere and everywhen, that the universe is fundamentally comprehensible, governed by knowable principles. and this comprehensibility is itself mysterious. Why should the universe be governed by mathematical laws? Why should those laws be discoverable by creatures like us, evolved to survive on a small planet, not to understand quantum mechanics or cosmology? And yet we can understand, partially at least. We can do experiments, develop theories, make predictions, and find that the predictions match reality. This works. This process of science works. And it's given us knowledge about the nature of reality that would have seemed like magic to our ancestors, knowledge that seems like magic even now when you really think about it. You're thinking about it now, or you were. But perhaps your thoughts are becoming less focused, drifting, dissolving into fragmentary images and feelings, and that's perfect. That's exactly what should happen. Thoughts arise and pass away, like particles in the quantum vacuum, appearing and disappearing, and you don't need to hold on to them. Let me tell you something about photons again, but more softly this time, more slowly. A photon is a quantum of light, a particle, but it's also a wave in the electromagnetic field, an oscillation that extends through space. When a photon is created, perhaps by an electron dropping to a lower energy level in an atom, the photon doesn't have a specific location. It's spread out, and as it travels it continues to be spread out, described by a wave function that evolves through space and time. If the photon encounters a detector, an atom that can absorb it, the wave function collapses, and the photon is detected at a specific location, delivering its energy to that atom. Before detection, the photon was nowhere in particular. After detection, it was definitely at the detector. But what about in between? What was the photon doing while it traveled? Quantum mechanics doesn't answer this question, or rather it says the question is misguided, that there's no fact of the matter about what the photon was doing when it wasn't being observed. This is unsettling, but it's the nature of quantum reality. Things don't have definite properties except in relation to measurements, to interactions with other systems. And perhaps this is freeing in a way. It means that reality is not a collection of isolated facts, determined and definite, but a web of relationships, potentialities that become actual through interaction. Everything is connected to everything else, not in a vague metaphorical sense, but in a precise physical sense, through the quantum fields and the entanglements they create, through the shared history of particles that have interacted, through the common origin of all matter and energy in the Big Bang. You're connected to all of this. Connected to the stars, because the atoms in your body were made in stars. Connected to the quantum vacuum, because your atoms are constantly interacting with virtual particles. Connected to the distant past, because the photons you see have traveled for millions or billions of years from their sources. There's no true separation, only apparent separation, patterns that seem distinct, but are all part of the same underlying quantum reality, the same wave function of the universe, evolving according to the Schrödinger equation, branching perhaps into many worlds, or collapsing in moments of measurement, or both, or neither, depending on which interpretation you prefer. But the mathematics is the same, the predictions are the same, and the mystery is the same. The deep question of why there is something rather than nothing, why the universe exists at all, why it follows these particular quantum rules and not others, or no rules at all. These are questions that physics might never answer, questions that might be beyond the scope of science, belonging instead to philosophy or theology, or the realm of unanswerable mysteries. And that's all right, too. Not everything needs to be answered. Some questions are worth asking, even if they have no answer, because the asking itself is meaningful, because it reflects something deep about human nature, our curiosity, our desire to understand. You've been curious tonight, listening to these thoughts about quantum mechanics, and perhaps you've absorbed something, some sense of the strangeness and beauty of the quantum world, or perhaps you've absorbed nothing and simply let the words wash over you, and either way is fine. The universe doesn't require your understanding. It continues regardless, stars burning, galaxies rotating, particles interacting, following the quantum dance that has no audience, needs no observer, simply is. And you're part of that dance, your atoms trading energy with the environment, your molecules vibrating, your cells metabolizing, your brain processing, all of it quantum mechanical, all of it following the same rules that govern everything else. There's a kind of democracy to quantum mechanics, a sense in which everything is fundamentally the same. All electrons are identical. All photons of the same energy are identical. The distinctions we see between living and non-living, between conscious and unconscious, between important and unimportant, these are distinctions we impose, categories we create. But at the quantum level, there's just matter and energy, particles and fields, all following the same laws. This doesn't diminish the importance of those higher-level distinctions. Life is genuinely different from non-life, even if both are made of the same quantum ingredients. Consciousness is genuinely special, even if it emerges from quantum processes in neurons. The categories we create are real and meaningful, even if they're not fundamental. But it does provide a kind of perspective, a reminder that we're not separate from nature, not outside the physical universe looking in, but deeply embedded in it, made of it, continuous with it. When you look at a tree, you're looking at organized sunlight. The tree captured photons from the sun, quantum particles of light, and used their energy to build molecules, to grow, and those molecules came from carbon dioxide in the air and water from the soil, and the whole process is driven by quantum mechanics. By the way, electrons in chlorophyll molecules can absorb photons and enter excited states and transfer that excitation through chains of reactions. When you eat food, you're consuming organized quantum energy, breaking down molecules and extracting the energy stored in their chemical bonds, energy that ultimately came from the sun, from nuclear fusion in the sun's core, where quantum tunneling allows protons to overcome their mutual repulsion and fuse together. Everything is sunlight, transformed and reorganized. Everything is quantum mechanics, playing out in endlessly creative ways, building structures of greater and greater complexity, from atoms to molecules to cells to organisms to ecosystems to civilizations, all of it emerging from the same simple quantum rules. And now, some of those organisms, some of those temporary patterns of organized energy, have become complex enough to understand the rules, to figure out quantum mechanics, to peer into the foundations of their own existence. This is extraordinary when you think about it. The universe has become conscious of itself, aware of its own nature, through the process of evolution creating brains capable of doing physics, mathematics, philosophy. You are one such brain, one such pattern of consciousness, lying here in the darkness or the dim light, thinking these thoughts, or having stopped thinking and drifted into some other state, some twilight zone between waking and sleep. And in that twilight zone, perhaps quantum mechanics becomes more intuitive, not less. In dreams, things can be in multiple states at once. Locations shift and blend. Identities are fluid. Causality becomes loose. The normal rules are suspended, and something more quantum-like emerges. Of course, dreams aren't actually quantum mechanical in any technical sense. They're classical neural processes, even if those processes ultimately rest on quantum foundations. But there's a poetry to the comparison, a sense in which the dream state reflects something about the fundamental ambiguity of quantum reality. Let's think about particles again, but this time about their creation and destruction. In quantum field theory, particles aren't permanent things. They can be created and destroyed, appearing and disappearing as the fields oscillate and interact. When two particles collide at high energy, like in a particle accelerator, they can create new particles that didn't exist before. The kinetic energy of the collision gets converted into mass, into the creation of new particles, in accordance with E equals mc squared. And when a particle meets its antiparticle, they can annihilate, both disappearing and converting their mass back into pure energy, usually in the form of photons. This means that the identity of particles is not permanent. The specific electron in a specific atom might not be the same electron that was there a moment ago. Particles of the same type are identical and interchangeable, and there's no way to tag an electron, no way to follow its history and say this is the same electron I saw before. In fact, there's a sense in which all electrons might be the same electron, the electron field in different excitation states, or in an even stranger idea proposed by physicist John Wheeler, all electrons might literally be the same electron, moving forward and backward in time, appearing in many places and many times, but always the same single entity, viewed from different temporal perspectives. This idea probably isn't correct, but it's beautiful, and it illustrates how quantum mechanics and relativity together allow for strange possibilities, temporal loops and backward causation, and all sorts of things that seem impossible in classical physics. The relationship between quantum mechanics and time is deep and subtle. The Schrödinger equation describes how quantum states evolve in time, but it treats time differently from space. Time is a parameter, an external framework, while space is part of what the wave function describes. But in relativity, time and space are unified into space-time, a four-dimensional structure where the distinction between time and space is somewhat arbitrary, depending on your reference frame, how you're moving. Combining quantum mechanics with relativity required developing quantum field theory, and that was a triumph, explaining so much about particle physics and forces. But combining quantum mechanics with general relativity, Einstein's theory of gravity, where spacetime itself is curved and dynamic, has proven much harder. The problem is that general relativity is classical, describing spacetime as a smooth continuum, while quantum mechanics deals with discrete, granular phenomena. When you try to quantize gravity, to apply quantum mechanics to the gravitational field, you get mathematical problems, infinities that can't be removed with the standard techniques. String theory tries to solve this by replacing point particles with extended objects, strings, that vibrate at different frequencies. The different vibration modes correspond to different particles, and one of these modes corresponds to the graviton, the hypothetical quantum particle of gravity. String theory requires extra dimensions of space, beyond the three we experience, 6 or 7 extra dimensions curled up so small that we don't notice them. This sounds bizarre, but it's mathematically consistent, and it's one of the few approaches that seems to avoid the infinities that plague other attempts at quantum gravity. But string theory is also incomplete, or at least we don't fully understand it yet. There are different versions of string theory, different ways the extra dimensions can be configured, and we don't know which, if any, describes our universe. And there's essentially no experimental evidence for string theory because the energies needed to directly test its predictions are far beyond what we can achieve in particle accelerators. So string theory remains speculative, promising but unproven. Loop quantum gravity takes a different approach, keeping four-dimensional space-time but suggesting that at the smallest scales, at the Planck scale, space-time is not continuous but discrete, made of tiny loops or networks, quantum geometry. In this view, space itself comes in minimum chunks, quanta of volume, and time comes in minimum durations, quanta of time, and the smooth spacetime of general relativity emerges as an approximation when you average over many of these discrete chunks. This also avoids some of the infinities that plague quantum gravity, but it has its own challenges, and like string theory, it's difficult to test experimentally. So the question of how to unify quantum mechanics and gravity remains open, one of the deepest unsolved problems in physics, and it's connected to other mysteries, like the origin of the universe, the nature of black holes, the possibility of time travel. Inside a black hole, gravity is so strong that spacetime curves so much that nothing, not even light, can escape. At the center of a black hole is a singularity, a point where the curvature becomes infinite, where general relativity breaks down and quantum effects should become important. But we don't have a theory of quantum gravity to describe what happens there. The singularity is hidden behind the event horizon, the boundary beyond which nothing can escape, so we can't observe it directly, but theoretically it represents a place where our current physics fails, where we need new ideas. Similarly, at the Big Bang, the universe was compressed to an extremely small size and high density, and quantum gravitational effects should have been important. Understanding the very first moments of the universe requires a theory of quantum gravity that we don't yet have. So there are fundamental limits to our current knowledge, places where we can't yet see, questions we can't yet answer. And that's humbling. It's a reminder that despite all we've learned, despite the incredible success of quantum mechanics and general relativity, we're still far from a complete understanding. But every generation has faced such limits, and every generation has pushed them back a little further, discovering new layers of reality, new principles, new connections. There's no reason to think we've reached the end of that process. Your breathing has perhaps become slower, deeper, more rhythmic. Your body knows how to relax, knows how to transition into sleep, and it's doing that now. Automatic processes taking over, consciousness fading into the background. And all of those processes, the slowing of your heart rate, the change in your brain waves, the relaxation of your muscles, all of them are ultimately quantum mechanical, electrons and atoms and molecules following the Schrödinger equation, even though the overall behavior is classical enough that doctors can measure it with ordinary instruments. This is the mystery of emergence, how quantum mechanics, which is probabilistic and weird, gives rise to classical behavior, which is deterministic and familiar, at least approximately. The answer has to do with decoherence, which we've mentioned before, and with the law of large numbers, the fact that when you average over enormous numbers of quantum particles, the quantum fluctuations tend to cancel out, leaving predictable classical behavior. It's like flipping a coin. One flip is random, completely unpredictable. But flip a coin 1,000,000 times, and you'll get very close to exactly half heads and half tails. The randomness is still there in each individual flip, but it averages out in the aggregate. Similarly, your body is made of so many atoms, so many quantum particles, that the quantum randomness averages out, and what remains is classical, predictable, reliable enough that you don't quantum tunnel through the floor or spontaneously disintegrate into a cloud of particles. But the quantum nature is still there, underneath, and occasionally it matters. Genetic mutations, for instance, can be caused by quantum tunneling, where a proton in a DNA molecule tunnels to a slightly different position, changing the structure of the molecule and potentially leading to a different amino acid being coded for. These mutations are random, quantum events, and they're one of the sources of variation that drives evolution. So in a very real sense, the diversity of life on Earth, the process of evolution that created you and every other living thing, is partly driven by quantum mechanics. Randomness at the quantum level becomes variation at the biological level, becomes natural selection, becomes evolution, becomes the incredible diversity and complexity of the biosphere. It's all connected, quantum mechanics to chemistry to biology to ecology, each level building on the one below. Each level with its own patterns and principles, but constrained by the levels beneath. You are the product of billions of years of this layered complexity, starting with quantum fluctuations in the early universe, becoming galaxies and stars, becoming heavier elements forged in stellar cores, becoming planets and oceans, becoming organic molecules, becoming self-replicating systems, becoming cells, becoming multicellular organisms, becoming nervous systems, becoming brains capable of thought and feeling and understanding. And now, here you are, the universe looking at itself, a temporary pattern of organized complexity that emerged from quantum mechanics and will eventually dissolve back into it, but for now is aware, experiencing, thinking about quantum mechanics itself. There's something circular about this, something self-referential and strange. Quantum mechanics is understood by brains made of quantum particles. The theory describes the very processes that allow the theory to be understood. This circularity appears throughout science and philosophy. We use our minds to understand our minds. We use language to analyze language. We use mathematics to study the foundations of mathematics. And quantum mechanics adds another layer to this, because it suggests that observation is not separate from reality but part of it, that the act of understanding changes what is being understood, or at least brings it into a definite state from a superposition of possibilities. So perhaps in understanding quantum mechanics, we're participating in the universe's process of defining itself, of collapsing wave functions, of bringing potentialities into actuality. Or perhaps that's too mystical, too much of a stretch. Perhaps quantum mechanics is just a theory, a mathematical tool that predicts experimental results, and observation is just a physical process, an interaction between systems, with nothing especially profound about it. Both views are possible. Both can be held simultaneously, like a superposition of interpretations, and maybe the truth is somewhere in between, or somewhere else entirely, in a direction we haven't thought of yet. Let the questions dissolve. Let the uncertainty be okay. You don't need answers tonight. You don't need to resolve the measurement problem or unify quantum mechanics with gravity or decide between interpretations. You can simply rest in the mystery, in the strangeness of existence, in the fact that anything exists at all, and that it follows quantum rules, and that those rules have led to you, here, now, thinking these thoughts or drifting past them into sleep. The room around you is dark, or dim, and quiet, or filled with soft sounds, and comfortable, or comfortable enough, and all of it, every bit of it, is quantum mechanical. Atoms and molecules in their ground states and excited states, photons bouncing around or being absorbed, thermal energy distributing itself according to the laws of thermodynamics and quantum statistics. Even the darkness is not empty. It's filled with thermal radiation, infrared photons emitted by everything in the room, by the walls and the floor and your own body, all at a temperature above absolute zero, all radiating. You can't see this radiation because your eyes aren't sensitive to infrared, but it's there, a gentle glow of quantum thermal energy. And the air is full of molecules, nitrogen and oxygen mostly, bouncing around in random thermal motion, constantly colliding with each other and with the surfaces around them, creating air pressure, creating sound waves when something vibrates, carrying thermal energy from warmer places to cooler places. Each molecule is a quantum system, with vibrational modes and rotational modes, quantized energy levels that the molecule can occupy. At room temperature, many of these modes are excited, with molecules vibrating and rotating in complex patterns, all governed by quantum mechanics, and yet the overall behavior is classical enough that we can describe it with simple laws, the ideal gas law, thermodynamics, classical mechanics. The quantum details wash out, become invisible in the aggregate, leaving simple relationships between pressure and volume and temperature. This is how the universe works at every level, quantum at the bottom, increasingly classical as you move to larger scales, with each scale having its own appropriate description, its own effective theory. And you don't need to understand all the scales at once. You can understand each level on its own terms, using the concepts and principles appropriate to that level, and that's enough for most purposes. You don't need to think about quantum mechanics to live your life, to make decisions, to interact with people and objects. The classical world is real and valid, even if it emerges from a quantum foundation. But sometimes it's worth remembering the foundation, worth thinking about the strangeness underneath the familiar, the deep principles that govern everything, the quantum rules that have been playing out since the beginning of time and will continue until the end. If there is an end. The universe might be eternal, or it might have a beginning and an end. We don't know. The Big Bang seems to mark a beginning, but maybe there was something before the Big Bang, another universe or a different phase of this universe, collapsing and rebounding in an endless cycle. Or maybe time itself began at the Big Bang, and there is no before, and the question of what came before is meaningless, like asking what's north of the North Pole. These are cosmological questions, questions about the universe as a whole, and quantum mechanics plays a role in trying to answer them, because the early universe was small enough and dense enough that quantum effects were crucial. The tiny quantum fluctuations in the very early universe, stretched by the rapid expansion called inflation, are thought to have become the seeds of all structure, the slight variations in density that eventually collapsed under gravity to form galaxies and stars. So the quantum and the cosmic are connected. The very small and the very large both require quantum thinking. Both resist simple classical explanation. And somewhere in between, at human scales, at the scales of everyday objects, the quantum becomes classical, the cosmic becomes local, and we live our lives mostly unaware of the strange foundations and the vast context, but connected to both nonetheless. You're connected to the stars through the atoms in your body. You're connected to the quantum vacuum through the fields that fill space. You're connected to the beginning of time through the history of those atoms and those fields, all the way back to the Big Bang and perhaps beyond. Everything has a history, a lineage, a story of how it came to be. Your story includes the formation of the solar system 4.5 billion years ago, the emergence of life on Earth 3.5 billion years ago, the evolution of your particular species over millions of years, the lives of your ancestors, the specific chain of events that led to your existence. And underneath all of that, supporting all of that, is quantum mechanics, the framework within which chemistry and biology and everything else happens, the rules that make atoms stable and molecules possible and life inevitable, or at least not impossible. If the quantum rules were different, if the constants of nature had different values, if electrons had different masses or charges, the universe would be unrecognizably different. Atoms might not form, or stars might not shine, or chemistry might be too simple to support life. The fact that the universe has the particular properties it does, properties that allow for complexity in life and consciousness, is sometimes called the fine-tuning problem. Why is the universe hospitable to life? Why do the constants have the values they do? Some people see this as evidence for design, for a creator who chose the constants carefully. Others invoke the anthropic principle, the idea that we observe a universe compatible with our existence, because we couldn't exist in a universe that wasn't compatible. Or perhaps there are many universes, a multiverse, with different constants in each one, and we happen to exist in one of the universes where the constants allow for life. This is speculative, but it's consistent with some interpretations of quantum mechanics, like the many worlds interpretation, where every quantum possibility is realized in some branch of reality. So maybe every possible universe exists, somewhere, and we're in this one, because this one has the right properties, and there's nothing more to explain than that. Or maybe there's a deeper principle, some reason why the constants have the values they do, something we haven't discovered yet. These are big questions, ultimate questions, and they might not have answers, or at least not answers we can ever verify, but they're worth thinking about, worth wondering about, because they touch on the deepest mysteries of existence. And even if we can't answer them, we can appreciate them, appreciate the strangeness and beauty of the fact that we're here to ask them, that the universe has become conscious of itself through us, that quantum mechanics has led to creatures capable of understanding quantum mechanics. This is extraordinary, genuinely extraordinary, and it's easy to lose sight of in the routine of daily life. But moments like this, moments of quiet reflection, can help bring it back into focus, help remind us of the larger context, the deeper reality. You're part of something vast and ancient and ongoing, the universe's exploration of itself, the quantum dance of matter and energy that's been happening for billions of years and will continue for billions more. Creating patterns, dissolving patterns, creating new patterns, endlessly creative, endlessly surprising. And for a brief moment, you're one of those patterns, aware and thinking and feeling, experiencing what it's like to be a localized structure of organized energy in a quantum universe. Soon you'll sleep, and consciousness will fade, and the organized patterns in your brain will loosen, entering different configurations, dream states perhaps, or deep dreamless sleep where consciousness is minimal or absent. But you'll still be there. Your body still functioning, quantum processes still running, keeping you alive through the night until you wake again, and consciousness returns and you're able to think and act and experience once more. This cycle of waking and sleeping has repeated every day of your life, and it will continue until it doesn't, until the pattern that is you finally dissolves, your atoms scattering and becoming parts of other things, other patterns, continuing the endless dance. But that's far away, in the future, and right now you're here, comfortable and relaxed, breathing slowly, drifting towards sleep, and all is well, all is as it should be, the quantum universe humming along beneath everything, reliable and strange, mathematical and mysterious, the foundation of all that is. Let yourself sink deeper now. Let the words become just sounds, rhythmic and soft, carrying no meaning, requiring no attention. Let your mind wander where it will, or nowhere at all, into the gentle darkness, the quantum void from which all things arise and to which all things return. You are stardust, quantum fluctuations, organized into this particular form for this brief time, and that is enough. That is everything, that is the miracle and the mystery, and you can rest in it, float in it, dissolve into it, knowing that you are part of the great quantum whole, connected to everything, temporary and eternal, real and dreamlike, here and everywhere, now and always. The universe breathes through you, and you through it. And the distinction between self and other, between inside and outside, becomes less clear, less important, as consciousness fades and sleep approaches and the quantum dance continues, as it always has, as it always will, in you and through you and beyond you, forever and ever, the endless quantum dream of existence, beautiful and strange, comforting and mysterious, everything and nothing, all at once. Rest now. There is nothing to do, nothing to understand, nothing to remember, only the gentle rhythm of being, the quiet hum of quantum reality, the soft darkness welcoming you home.